Hi, this is going to be ENGPHYS 3004 Tutorial 3, the video. So what we're going to be doing is solving problems in the first part of chapter 14 in the textbook. This is dealing with sources of frictional head loss and ways to calculate that given straight pipe sections in either laminar or turbulent flow. So first one we have is probably the hardest one. It's 6 marks. I guess there's 2 different parts of this which add up to 6. But this question can be extremely difficult, but there is a trick to doing it. So we're going to explain both ways. A 500 meter long section of water main carries water at 10 degrees C to a neighborhood. If the water main is made of commercial steel, determine the required pipe diameter to be able to maintain a volume flow rate of 1 cubic meter per second with only 1 meter of head loss. Be sure to verify that your method was valid, i.e. check that any Reynolds number and roughness assumptions were justified. So they don't tell us the properties of the water at 10 degrees C, so we're going to have to look those up. If the question bothers to tell us the temperature, then the more detailed properties of water are probably going to be important. Otherwise, if they just said water, we could probably assume some temperature and guess. The other thing that makes this question kind of difficult is that they don't tell us the diameter. So not knowing the diameter is going to mean that there's a number of there's multiple numeric steps in order to do this question exactly right. Okay, so we've got our water properties looked up from the back of the textbook, the dynamic viscosity and the density of water. Now, to deal with this question, we're going to need to bring in some equations. So let's start off with the head loss equation. And then you see that we're going to need the friction factor for this. So for the friction factor equation, we need to know whether we're dealing with a laminar flow or a turbulent flow. And because it's water, because it's a big flow rate and we don't want much head loss, so over a long pipe section, it's almost certainly going to be turbulent. This is going to require a large pipe. So we're going to initially guess that we have a turbulent flow and then use something like the Colebrook equation in order to deal with what's with this problem. And then we'll come back and check whether or not the system was actually turbulent, whether or not the Reynolds number justified that. So the Reynolds number is rho VD over mu, and these equations are in terms of velocity, but we don't actually have velocity in the problem. And what makes this really tricky is that we can't even calculate the velocity exactly. We know that the velocity times the area is the volumetric flow rate, which we do know. So in other words, the velocity is equal to the volumetric flow rate divided by the area, which is pi d squared over 4. So in other words, it's 4 volumetric flow rate over pi d squared. Now we're going to need this in a couple of different spots. So in Reynolds number, we'd have to write that the Reynolds number is mu, or rather rho, times, let's see, for volumetric flow rate, one of the diameters is canceling, and we're going to have pi mu d left over. That should work. So we just substituted this in for the velocity there, and then let one of the diameters cancel. And then doing something similar with the pressure loss equation. We're going to have this thing squared. So 4 volumetric flow rate over pi d squared, now all squared. So that means, what are we going to have? Pi d to the 5/16 volumetric flow rate squared. Okay, this equation we can rearrange to solve for what the diameter would be. It looks like diameter, according to this equation, is going to be, is going to be the 5th root. So I'm going to imagine that we've brought diameter over to this side and then brought this stuff down in the denominator on the left. And so we've got that gone, but we've got a GHL still there. And that's what we end up with. Okay, so diameter is the 5th root of, whoops, isolated it, yeah, of this thing. So friction factor 16L over pi, volumetric flow rate squared over 2 GHL. And we know everything in here except for the friction factor, which unfortunately in this question is, if we use the Colebrook equation, is in another, comes from another equation, which is iterative in F, and in addition to that depends on the diameter. So we've got rho for volumetric flow rate over pi mu times diameter. So diameter shows up twice in this equation, and then we would have to use this equation to iterate in order to find F. So let's go through a couple of different ways to deal with this problem, which is kind of has us going back and forth here. So first, let's talk about the kind of most extreme way to go through this, and this would be the just doing iteration manually all the way along. So what we'll do is substitute in what we know to these equations. So the 16 over 2 is just going to be 8, and we're going to multiply by 500 meters. The volumetric flow rate was just 1 cubic meter per second. G is 9.81 meters per second squared, and the head loss was 1 meter. Okay, so just a quick unit check. We've got per second squared in the numerator, per second squared in the denominator, so those are gone. Meters to the 6 divided by meters squared times meters is meters to the 7 over meter squared, meters to the 5th. So 5th root will give us, yes, diameter. Okay, all good. And we can calculate what this thing is. So 8 times 500 divided by 3.14159 times 2 times 9.81, and we've got 64.895. And then we could take the 5th root of that, or just leave it under the root thing there. That's totally fine. All right, so let's say diameter is equal to that thing to the power of 1 over 5 after we also multiply in a friction factor. So we'll say diameter is equal to the friction factor times that whole thing, all raised to the power of 1/5. And we don't know what, we need a friction factor to do this, so let's just pick one. If we go over to the chart, then you see friction factors range between 0.01 for very smooth pipes. If the roughness is higher, then we're forced to have higher friction factors. And in the roughness chart, I think, did they say in the question this is a steel pipe? Commercial steel. Okay. So commercial steel has a roughness of 0.045 millimeters. And so really we'd need the relative roughness to know how that compares to the diameter. 0.045 millimeters. If we guess the diameter is going to be something like 1 meter, then 0.045 millimeters is an extremely low epsilon over d. So maybe we're looking at a friction factor on the order of 0.01. So let's just initially see if that works. So this is actually 0.01, our initial guess. We're going to come back and change this in a minute, but for now we can use that to find the diameter. So the diameter is, yeah, close to 1 meter according to that calculation. And now the next part is we want to take that diameter and go and substitute it into the one of our expressions for the friction factor. The hardcore way to do this is to go right into the Colebrook equation here and calculate that out with iteration to really narrow in on the friction factor. But since the diameter is an initial estimate at this point, it doesn't make too much sense to use the Colebrook equation really. I mean, if you have Maple, you can use fsolve and get it numerically, but we may as well just use the Haaland equation instead, which is at least explicit in the friction factor. So that would be substituting in rho for volumetric flow rate over pi mu d. Okay. So coming back over here, we're going to have our next F guess is from solving this thing for F, which would be what you get if you take 1 over each side and then square both sides. So F is going to be 1.8 times log 10 of 6.9 times 3.14159 times the diameter that we just calculated divided by rho. Maybe we'll type rho in. Rho is 999.7, and mu is, we're also going to need mu, which is 1.3070 minus 3. Okay. So where were we? Divided by rho times 4 times 1 plus epsilon over d. So 0. The commercial steel roughness 0.045 E minus 3. Let's remember this is in millimeters. 0.045 E minus 3 divided by the diameter, and then divided by 3.7. Maple's order of operations will put this on the denominator of that whole equation to the power of 1.11. And there's our next F guess, perhaps. Okay, so we're missing a bracket. Ah, yeah, we wanted to take that whole thing and then square it. Oh, so there's something wrong here because that's way too big for friction factor. Something is definitely incorrect here. So I'm going to look around this equation. You can pause the video here if you want to figure out what went wrong. Well, okay, one mistake is when we were writing this formula out, when we canceled the 16 with the 2, we actually forgot to remove the 2. So that's got to go, and that changes the first equation a bit. So we're not going to have that 2 up there. We still have a friction factor that's quite large. So double checking this equation, should have 6.9. Oh, we didn't put in the mu, did we? Yeah. Okay. Oh, That's not good. That's moving in the wrong direction there. Ah, you know what else? We needed 1 over this whole equation. So we'll take this whole thing to the power of -2. Ah, that's more like it. So this is like the friction factor that we were expecting of around 0.01. That makes more sense. For this kind of a diameter, we needed that kind of a friction factor. As per usual, in these sorts of calculations, extremely easy to make some very big mistake. Fortunately, this time the mistake was so big that it made our answer ridiculous, so we were able to catch that. Anyway, where's the iteration come into this? Well, what you do is something like this, and now we calculate the diameter. So we sort of guessed the friction factor of 0.01, use that to find the diameter, then use that to find the friction factor, then use that one to find the diameter, and then to find the friction factor, diameter, friction factor, diameter, friction factor. So the friction factor actually didn't change very much after the first time. You see now we're in these very far in decimal points. And there's no point in getting that much precision with it, since the Haaland equation is not guaranteed to be that accurate anyway. So so we're all right. We're in pretty good shape here. If you wanted to know how much better or how much worse this is than the Colebrook equation in this case, then we can do another version of the problem where we use Colebrook equation. So how would that be different? Well, for this step, instead of doing that, what we'll do is solve the explicit equation. You could include some iteration on that. So this is the Colebrook equation, and what we'll do is say f is equal to, if you have maple, f solve -2 1 over square root of f is equal to -2 times log 10 of 0.045 e minus 3 divided by diameter divided by 3.7 plus 2.51 times pi times mu times diameter divided by rho times 4 times 1 times the square root of f. Close out that logarithm, and then we can give f solve a range. .005 to 0.1. Maybe this huge range. See if that's good. Okay, let's check brackets here. We took this divided by that, and then we need to close out the logarithm here. Invalid arguments in f solve. So we gave it a thing. Oh, right. In f solve, we can't. We now wouldn't assign a parameter. So okay, this thing actually was able to f solve using its numerics. Was able to do some really nuts stuff where you just take the diameter in terms of the friction factor, sub that into here, and then f solve don't care. It can be as you don't need this iterative solution. It's able to solve all the way through and get the real friction factor, and then sub that back into the diameter expression at the end. So diameter is 1.105 and the friction factor is 0.0126. How close did we get before? 1.102 and 0.0125. So almost the same using this simpler Haaland equation and the iterative method than the numeric solving. And the last thing that I want to bring up is the way that you should actually do it on this test, and that is to not use any of these equations, but instead just jump right to this explicit equation. Because we have a circular pipe, you can use this approximate equation. which is awesome because it lets you just substitute in everything directly and then tells you what the diameter will be. So this is only valid for certain ranges of Reynolds number and relative roughness. So we can check at the end whether or not it was going to work. Okay, so with this equation, now not knowing the friction factor, we'll say that the diameter is 0.66 times epsilon 0.045 e minus 3 to the power of 1.25 times L. Put in L. L is 500. Yeah. L, volume flow rate is 1 divided by, we'll put in G as well, over G. Head loss is 1 to the power of 4.75 plus, the nu here is the kinematic viscosity, which is the dynamic viscosity divided by density. So that would be mu over rho. So we'll put nu times volumetric flow rate, which again is 1, times L over G to the power of 5.2. And this whole thing is going to be to the power of 0.04. Let's see how we do with this. So this equation, if we've typed it in correctly here, 0.66 times 0.045 e minus 3 to the power of 1.25 times L over G times to the power of 4.75 plus nu, and then flow rate to the 9.4 times L over G to the power of 5.2, all to the power of 0.04, has given us an answer that is not so great compared to the calculation that we did above using iteration. Okay, so to recap, we used the approximate equation here, and we found out that the diameter should be like 0.88, where you just type in this equation and get the diameter, 0.88. But we used the previous complicated iterative method, and we found out the diameter should be 1.1. So we're actually way off. This equation looks terrible, right? Well, let's explore that a little bit. So although this equation has more approximation built into it and is not guaranteed to be as accurate as the other ones, it should be more accurate than this, which means we probably dealt with the approximation in the first one that shows up when we make math errors. I've paused the video and had gone and looked over it a bit. In order to deal with this, what I did is first kind of went back to the drawing board and just took these two basic equations at the start, and then using a more maple-y way of solving it, typed in the head loss, the area in terms of the diameter, the velocity in terms of the flow rate in the area, density, dynamic viscosity, length, G, roughness, typed in equation 1, which is this one, typed in equation 2, the Colebrook, and then typed in what the Reynolds number is and told it to explicitly go and solve this. And when you do that, you find an answer which is much closer to the one that we got using the approximate equation rather than the one that we got by doing iteration. So after looking things over more carefully in this first set of equations, I did catch one issue, which was to do with this. So maybe you noticed this at the time, and kudos to you if so, but I dropped a square on the pi term. So what that means is that the answer we calculated would be off by the inverse of the 5th root of pi, which doing the calculation again, we put a 1 there. That's the answer we got before. Inverse of the 5th root of pi is just enough to get us much closer to the approximate thing that we got with that other formula. So just because the formula is, well, I guess we should say just because this iterative solution method or fancy combined fsolve method is a lot more robust than just using a simple version of the formula, it can't make up for mistakes that you're going to make in the math along the way to substituting it in. Moving on. How does roughness affect flow energy loss to heat in laminar and turbulent flow? Okay, so the Moody chart is a quick kind of talk through and reminder of how this stuff works. The head loss equation up here says that the head loss is directly proportional to this friction factor, and the head loss is what's going into heat. So the friction loss to heat is increasing with the friction factor, and friction factor is doesn't depend on roughness for laminar flow, because in laminar flow the no-slip condition at the walls and the smooth streamlines mean that the wall is just the flow near the walls is just kind of guiding along the roughness, and the kind of not affecting the flow right next to it nearly to the same extent as in turbulent flow, where you have a lot of lateral momentum transfer along the way. So in turbulence, the roughness has a large effect on the frictional energy loss to heat, but in laminar flow, roughness doesn't matter at all. So to maybe be more specific on that, in turbulence, the really low levels of relative roughness don't make a difference until you go to higher and higher Reynolds number. So at a Reynolds number of 100,000 here, it doesn't make very much difference whether you have a relative roughness of 2 parts in 10 to the 2 parts in 10 to the 4 or 2 parts in 10 to the negative 4, right? So the difference between 0.002 and 0.0002, which would be somewhere around here, is almost nothing on this. The lines all get kind of crunched in, but that can make a difference if you're at a higher Reynolds number. So at a Reynolds number of 10 million, then that's a much larger difference in terms of the friction factor. So relative roughness above a certain point in turbulence can increase the friction factor until we get to a point where we're fully rough up to this kind of leveling off up here. Then below that, with less relative roughness, it only matters above a certain Reynolds number. And in laminar flow, it doesn't matter at all. One more question here. Water at 10 degrees C needs to be transported through a 1 meter long section of 1 centimeter diameter copper pipe. Find the head loss to friction if the flow rate is A, 1 liter per second, or B, 1 milliliter per second. So we have the length of the pipe, the water properties, and the diameter of the pipe this time. And they want us to determine the head loss for different flow rates, but one at a time. So using the same kind of setup as we had in the first part of this problem, now we're not going to need nearly as much detail in the iteration, because we're searching for the more basic version of this where we're finding the head loss and we know everything to find out what we need about the velocity. So we can put in the flow rate and use that to calculate the Reynolds number. Should copy down a Reynolds number formula first. And then based on that Reynolds number, decide if it's laminar or turbulent. And we will say, let's say the friction factor is going to equal this thing to the power of -2 in the case that the Reynolds number is greater than 4,000, and that would be turbulent, and is just going to equal 64 over the Reynolds number for a circular pipe if the Reynolds number is less than 2,300. Let's double check that we did that right. So yeah, laminar, you can see from your summary sheet, 64 over Reynolds number, and turbulent, something like the Colebrook equation or maybe the Haaland equation. All right, so first thing we're going to do is convert these flow rates into volumetric flow rates in SI units. Use those to determine what the Reynolds number and friction factor would be, and then use that to figure out the head loss from this last equation. So in terms of head loss, we can put it rearranged as so. In terms of flow rate, we could write something like the velocity times the area is equal to the volumetric flow rate, so that the velocity is the volumetric flow rate divided by the area, and the area is pi diameter squared over 4. So we can find out that area for this 1 centimeter diameter copper pipe. We can use these values to convert to volumetric flow rate. Let's think 1 liter per second. A liter is a cubic decimeter, so it's 0.1 meters per side. So this should be 0.1 meters cubed per second, which is equal to 1 e minus 3. Whoops. Don't want to get into that. Meters cubed per second. Okay, so that's the volumetric flow rate here. And this one is 1/1000th of that. So this should be 1 e minus 6 meters cubed per second. So check, this one 1,000 times bigger than that. 1 liter is 1,000 milliliters, so we're good to go. Okay, so that is how we could figure out what the velocity is. We take those velocities and the corresponding diameter to substitute into here to figure out the Reynolds number. Then based on the Reynolds number, we calculate the friction factor, and based on the friction factor, we can sub all that stuff into this equation to figure out what the head loss is. All right, let's get started. We will take the same water properties as last time. G is 9.81, and the area is 3.14159 times the diameter. I guess we'll put in that. Diameter is 0.01. Diameter squared over 4. Area looking like 79 e minus 6 square meters. Quite small, but it is a very small diameter. So we can use that along with the flow rate of 1 e minus 3 for now, which will change later, to figure out what the Reynolds number is. After we found the velocity. Okay, so in this first version of the problem, we've got a Reynolds number of 97,000, which means that we are going to be using the Colebrook equation to find out what the friction factor is. What do they tell us for the pipe? The pipe is copper, so yeah, the copper pipe is copper, which means that we can use a roughness of 0.0015. So back over here, epsilon is 0.0015 millimeters, and that means, let's first guess 0.01 and then do some iteration on this equation. So the next guess will be the whole thing to the power of -2 of 2. Since we're squaring it, we don't need to put the negative in front. Log 10 of epsilon over diameter over 3.7 plus 2.51 over the Reynolds number over the square root of f. Close out that logarithm, and that should be our next guess for the friction factor. And we don't expect it to go outside of the range of reasonable friction factors too much. That's one iteration. We can do the same calculation again and again and again in order to zero in on what friction factor we want. It seems like it's converged. On your calculator, you would just press the answer key a bunch of times in order to get that to work. So basically, not the answer key, the equals key. You type in the equation, you first evaluate something like this, and now that that's stored in the answer, you type in this equation so that it calculates it in terms of what the current answer is. Then you hit equals several times and it's going to recalculate. Quick way to do iteration on the calculator. All right, so that's the friction factor using Colebrook, and from that we can then calculate the head loss, which should be friction factor times L divided by diameter times V squared over 2 times G. And did we put in L? We did not. So L was 1. All right, that's simple enough. And so now we can reevaluate this again to see what 15.57 times 1 is. Gasp. 15.575 is the head loss. So 15.6 meters of head loss over just 1 meter of pipe, but it's a 1 centimeter diameter pipe, and we've got a fairly large flow rate through it of 1 liter per second. So that requires a fair bit of pressure in order to blast that water through. In the next version of the problem, we'd expect a much smaller flow rate. So let's just explore how this works. Same problem, except now the flow rate is 1e minus 6. So Reynolds number is 97. And that means we're going to change what we wrote before. Rather than caring about the roughness and using the Colebrook equation in laminar flow, the friction factor is just 64 divided by the Reynolds number. So the head loss this time has ended up being way, way smaller. Friction factor actually is larger than it was in the turbulent flow. Is that surprising? Well, not really. I mean, the friction factors do rise as you move further and further to the left as viscous effects become relatively more important compared to inertial effects. But because the head loss depends on the velocity squared and inverse with the diameter, the much smaller velocity from this much lower flow rate, velocity of 1 centimeter per second instead of 12.7 meters per second, has meant that we are moving at such a slow pace that the head loss is much, much smaller than last time.